In this example, we're asked to derive the differential equation of motion for the single degree of freedom system. The system's made up of a thin homogeneous bar. It's pinned to ground at O. And we're specifically asked to use the power equation to get to that point. In other words, what we want to do is write down the work energy equation for the system and then take a time derivative of that to extract our second order differential equation. In order to use the work energy equation, we need to know which forces, if any, do non-conservative work. So let's look at the FBD and make that decision. The forces that we have acting on this are OX and OY. These are reactions which are acting at pin O. And, of course, the weight of mg. Looking at these forces, we know that OX and OY do not do work. And the reason they don't do work is that they act at this point, which does not move. The weight force does do work, but we're going to include that in the potential U. So when we write down the work energy equation, what we will say is that energy, mechanical energy, is conserved. In other words, T, kinetic, plus potential U is equal to a constant. The kinetic energy for this, we could write this as 1/2 mvg squared, where, as defined there in the picture, g is the name given to the center of the mass of the bar, plus 1/2 mass moment of inertia about g times the omega squared, which in this case is theta dot squared. That's one way we could do it. Or, an alternate way would be simply to write down 1/2 mass moment of inertia about O times theta dot squared, where Ig, if we chose the first equation, we would use 1/12 ml squared. And if we use the second one, to use I.O., we would need to use the parallel axis theorem, which says Ig plus ml over 2 squared. Again, this is nothing other than using that relationship. So adding together a 12th and a 4th gives us a 3rd ml squared. The potential, the datum that I'm going to use is one which is passing through here. So whenever I write down the potential energy for the bar, I'm going to use a datum line which passes through the point O. So with that choice, then U becomes minus mg L over 2 cosine. And the reason the negative sign is there is really because the choice, a datum line that I used, and it happens that this is below the datum line. That's why we have a negative sign. So let's use the second one, because that's a simpler form for T. We have 1/2 I.O., which is 1/3 ml squared, theta dot squared, minus mg L over 2 cosine, and that is equal to a constant. The power equation is nothing other than taking a time derivative of this. The time derivative gives us the 1/6 ml squared times 2 theta dot theta double dot. That's coming from here. Minus mg L over 2, the derivative of cosine, is a negative sine sign with a theta dot in front like that. And of course the constant becomes a 0. So in the end, what we have is going to be, this will cancel out to a 1/3, and when I get through, I'm going to have 1/3 ml theta double dot plus mg over 2 sine theta times theta dot. And so at this point, we see that if we want something which is valid for all positions in all time, and we have theta dot multiplying this term here, theta dot's not going to be a 0 for all time, so we can strike out that and say that what we really need is this as a 0. So what we have here is 2/3. The m's will cancel out. In fact, let me do it two steps at one time. What I'm going to do is a theta double dot plus 3/2 g over L sine theta is a 0. This is the equation of motion for our single degree of freedom system there of the bar. We didn't have to deal with the reaction force there at all. In this case, it's a very minor thing. But what we were able to do, though, is get that second order differential equation straight away from looking at the conservation of energy for that bar.